Alright guys, so now we're going to take a look at the reaction quotient notes. So make sure you have your pink sheet ready to go. So reaction quotient is really a way to help us determine if a system is at equilibrium or not. So we've got some information here. It says graph A, so we're looking at, it's similar to the previous graph we looked at on our equilibrium reaction notes. We've got time A and time B and different concentrations. So first we've got to write our equilibrium expression for the reaction. I forgot to actually write the reaction on this one. So it is 2SO2 plus O2 forming 2SO3. They're all gases, so we're going to include them all. So our equilibrium expression would be our SO3 product squared over our SO2 reactant squared times our O2 reactant. So products over reactants, as you've practiced. And then number 2, it says to determine the equilibrium constant of the reaction. All right. I forgot to label all of this information on here with our concentrations. So our time B is actually here, and our time A is when these two are equal, O2 and SO2. So O2 and SO2. No, SO2, O2 and SO3 when they're equal. Here we go. So this is time A. Sorry about that. Figure this out. All right. So we want to figure out our equilibrium constant. So that would be at time B. So we're going to plug in our values for time B on here. So we've got 1.25 squared over 0.9 squared times 0.5. All right. So let's calculate this one out. 1.25 squared divided by 0.9 squared divided by 0.5. So we've got 2 sig figs, so 3.9 will be our equilibrium constant. So it says chemical concentrations for a reaction that is at equilibrium will always equal the equilibrium constant. So these concentrations at equilibrium will always give us the same constant. Even if a stress is applied to the reaction, so if we're shifting the reaction towards reactants or products, the reaction will shift to return to equilibrium. That's the whole idea behind Le Chatelier's principle that we looked at with the demonstration. We can determine if a set of concentrations are at equilibrium by plugging them into an equilibrium expression, solving, and then comparing the value to the equilibrium constant. Our comparison can help to determine which direction the reaction would need to shift to return to equilibrium. So do we need to get more products or more reactants to get back to that equilibrium constant? The chemical concentrations not at equilibrium are plugged into an equilibrium expression. We call the expression a reaction quotient. It's Q. It is written the same way, but with a different label. Okay, so notice that the entire thing on the right is exactly the same as our equilibrium expression. Same setup. We're just labeling it as Q. We label it as Q because we don't know if it's at equilibrium or not. Okay, we're saying, hey, this might be, it might not. We're just going to calculate the same way and see. So the only difference is the numbers. The only difference is the numbers that are put into the reaction quotient are concentrations that are not necessarily at equilibrium. We don't know. You can also set up a QP equation, so we can do it in terms of pressure, the same way we set up KP. So let's take a look. Number 3 says calculate the reaction quotient at time A for the reaction above. So we know, based on our information from our graph, that at point A we're not at equilibrium yet. So we're going to look at what that looks like in terms of our Q. So our Q expression looks exactly the same as our equilibrium expression. We're still going to have the products divided by the reactants with their exponents. And we're going to plug in the values from point A, time A in our graph. So at time A, our SO3 was 0.75. Our SO2 was 1.3. And our O2 was 0.75. All right. So we've got 0.75 squared divided by 1.3 squared, enter, divided by 0.75. Right, 0.443, etc. So 0.4426. So that is our reaction quotient value. That's basically the ratio of products to reactants at time A. So all it's showing us is that ratio. Once a value for Q is calculated, it can be compared to K to determine the direction the reaction will proceed and if it's at equilibrium. So remember, every reaction will react in a way to get to equilibrium. They will always return to that point. All right, so if Q is equal to K, they're the same value. You do all this and you get your Q value is the same as your equilibrium constant, then the reaction is at equilibrium. Those concentrations that you have, that ratio gives you equilibrium. Okay. If Q is greater than K, if the value you get here is greater than your equilibrium expression, then the concentration of the products is too large. Remember, this is products over reactants. So it's saying that if your Q value here is bigger than your K value, then you have too much stuff on the top. You have too many products. So you have a large numerator. To reduce the product concentration, so to get it to equilibrium and increase the reactants, the reaction will proceed towards the reactants or to the left to reach equilibrium. This will cause the numerator to decrease. So if we're going to shift it towards the reactants, we can think of like we're taking products and we're going to make some reactants. So this will decrease, this will increase. This case, the numerator will decrease, the denominator increases, and therefore reducing the Q value and getting closer to equilibrium. So it will do that, the reaction will do that constantly until it reaches equilibrium. That's why in our graph it continues to react until it becomes horizontal. All right, the last part, if Q is less than K. So if we're thinking about products over reactants, so if our Q value is less than our K value, that means that our number is too small. We have too big of a reactant. We have a large denominator. So to reduce the reactants and increase the products, we've got to shift some chemical towards the product or to the right to reach equilibrium. This will cause the denominator to decrease, the numerator to increase, therefore increasing the Q value and getting closer to equilibrium. So if Q is greater than K, it's going to go towards the reactants. So it's going to shift to the left. If Q is less than K, it has to shift to the right towards our products. And you can really always think through this and think about, okay, do I have a bigger product or reactants? Is my numerator too big or my denominator? You just got to kind of think through it. So if we look back at our two values, our equilibrium up here, our Q value is less than our K value. That means our number is too small. It needs to get bigger. So that means we have our denominator's too big. We have too much of it. We need to get bigger numerator. So that means it's got to shift. We've got to get less of this and we've got to make more of that. Well, since our products are on the top, it has to shift toward products. It's got to make more products. Well, if we look at our graph, if we start at point A, what are we making more of as we go? We're making more of the SO3. We're making more product. So it reaches equilibrium once we get more of that, and we use up some of that reactant. We had too much of it. Okay? So it's all just, how does it get back to equilibrium? When we do these shifts, how do we get back to our equilibrium? Okay? So let's take a look at some examples on the back. So at 448 degrees Celsius, the equilibrium constant for the reaction is 50.5. Predict which direction it will proceed to reach equilibrium if the following chemical concentrations are combined. So we want to figure out what it needs to do to get to equilibrium. So again, we need our products on the top, HI, it's going to be squared over H2, I2. Yep. All right, we're going to plug in our values. So HI is 0.010 over 0.0050 and 0.015. Put them in. So 0.01 squared divided by 0.005 divided by 0.015, 1.33. Or 1.3. Only one sig fig, or two sig figs. Okay, so now we're going to do our comparison. Q is 1.3, K is 50.5, so Q is less than K. This number is too small. So if we wanted to make this number bigger, we would need to shift and have smaller denominator, bigger numerator. We got to shift from the bottom to the top, which means we're going to shift toward the products, because the products are on the top, HI. Okay, let's try another one. At 1000 Kelvin, the value, or 1000, yeah, value of Kp for the reaction is 0.338. Calculate the value for Qp. Predict the direction of the reaction proceeds toward equilibrium if the initial pressure, partial pressures are the ones given here. Okay, so let's set it up for Qp. Just doing it in terms of pressure. So we've got pressure of our products, SO2. It's being squared. Pressure of O2 to the first power over the pressure of SO3 squared. Plug in our values. So SO2 is 0.41 atmospheres squared. Oxygen is 2.5 atmospheres. Pressure of SO3 is 0.16 atmospheres squared. All right, so we calculate 0.41 squared times 2.5 divided by 0.16 squared. I get 16. Let's see, we only got 2 sig figs, so 16. So now we do our comparison. K value is 0.338. So Q, being 16, is greater than K. So our Q is too big. Our values right now are not at equilibrium because it's too big. So we have too much up here. We got to shift it to the bottom. We got to get more on the denominator so we can reduce this number. So what's on the denominator? Our reactants. So it shifts toward our reactants. Okay. How about you pause, try this next one, last one, and then come back and check it. All right, hopefully you tried this last one. I'll walk through it now just in case you got stuck. So find the reaction quotient QC for this reaction. So H2S is our product over H2 reactant. And sulfur is a solid, so we're going to leave it out. So that means our H2S, 0.483 over 0.762 No exponents on this one. 0.483 divided by 0.762. 0.634. All right, we've got our K value. That has a times 10 to the 5th on it. That is a pretty big number here. So our K is, our Q is definitely less than our K value, much smaller. So if we needed this value to go up, we would have to do a major shift from denominator to numerator. We need a bigger top number. Our numerator is our product, so we need to shift toward product. Okay, so I kind of jumped ahead. So has the process established equilibrium? No, it definitely has not, because they're not equal. If not, which direction will it proceed? Shift towards the products. Justify your answer. Okay, so it shifts towards the products to increase the numerator and decrease the denominator in the ratio to reach equilibrium. Okay. So I think this is pretty straightforward. After you've done K, it's just comparing to K and really thinking about which number needs to get bigger. Do we need to get a bigger numerator or bigger denominator? And that's going to really tell you which way it's going to shift, because we know our products are on the top, reactants on the bottom. So your practice for this is just taking a look at writing some different expressions, doing some comparison there, and it's got down here, you're going to be circling whether it shifts left or right, whether and if it's shifting left or right, will that cause your Q to increase or decrease. And the back side is just more examples. So work through it. Again, put question marks next to the ones you get stuck on so we can go over